Welcome. This is module number 2 from our series on constraint optimization. The last module dealt with the method of Lagrange multipliers and how we could use that to solve constraint optimization problems with equality type constraints only. In this module, we're going to be discussing the Karush-Kuhn-Tucker conditions, which are going to allow us to solve constraint optimization problems with both inequality and equality type constraints. So let's define our Lagrange function again. Previously we had 4 components. We had our primal decision variables denoted by x, we had our objective function denoted by f, and we had our equality constraints denoted by g, as well as the Lagrange multipliers denoted by lambda. Now we're going to add inequality constraints, which will be denoted by h of x. And we're going to assume throughout this module that we're dealing with a less than or equal to inequality. And we also have to introduce a new Lagrange multiplier, mu, which is going to be associated with the inequality constraint. So if we take a look at the Lagrange function, we see that it still is additive, composed of our objective function plus lambda transpose times the equality constraints, plus or minus, we'll come back to that in 1 second, mu transpose times our inequality constraints. Okay, so why plus or minus right here? If we're assuming that h of x is less than or equal to 0, then this would be positive or a plus for minimization problems and a minus for maximization problems. For the most part, we're going to be focusing on minimization, which means this will be plus. Now the other note we have to highlight here is that mu must be greater than or equal to 0 for all of our inequality constraints. This differs slightly from lambda, on which we didn't really place any requirement or constraint like that. So how can we possibly solve this revised Lagrange function? Now we could try the process from before, right? Differentiate this new function, script L, set it equal to 0, and solve for the optimal state x sub OPT. However, we're going to see that step number 2 cannot be applied, at least as is, or not without some additional conditions. Why? Because differentiation with respect to the multiplier mu does not yield a function that is always equal to 0 for all feasible solutions. If you look down here, you can see we're taking the derivative of the Lagrange function with respect to mu. F is not a function of mu, so that goes away. Neither lambda nor g of x is a function of mu, so that goes away. And then down here, we're applying the product rule in order to find the derivative of essentially mu h of x with respect to mu. All right, and so these two elements are multiplied together, so we apply the product rule. Now the second chunk where we differentiate h of x with respect to u goes away because h is not a function of mu. But this piece right here remains, right? We have the derivative of mu with respect to mu, which obviously is going to give us a 1, and that leaves us with h of x over here. Now previously when we did this, in the last module, we ended up with g of x, and g of x is equal to 0 for the entire feasible region. So we could just go ahead and use that, but you'll see here that it's different with h of x, right? H of x is not equal to 0. It's less than or equal to 0. So if we constrain that to 0, we're essentially going to be over-constraining our problem and not potentially getting the most optimal solution. All right, so what can we do? We can apply the Karush-Kuhn-Tucker conditions, also known shorthand as the KKT conditions. They represent a generalization of the method of Lagrange multipliers, and they are required to consider the effect of inequality and equality constraints. And they're formulated as a set of necessary conditions, many of which are defined in terms of the first derivative. I'm actually going to X out this statement here because I don't like the wording, and simply state that the KKT conditions provide us a roadmap, okay, or a loosely defined method for solving this type of inequality constrained problem, and we have an example that we're going to use to exemplify this. Now, KKT is composed of 4 conditions. We have stationarity, primal feasibility, dual feasibility, and complementary slackness. So let's dive into what those are in more detail. Stationarity says that the gradient of the Lagrange function is expected to yield a solution beyond which no further optimization is possible. All that's really saying is when we differentiate the Lagrange function with respect to the primal state x, and we set it equal to 0, we're assuming that represents an extrema, and that is the optimal point. Primal feasibility simply says that all of the primal constraints, essentially g and h, must be satisfied by our optimal solution or optimal state. Dual feasibility says that for any Lagrange multipliers mu that are associated with inequality constraints, h, the following must apply. Essentially, the mu's must all be greater than or equal to 0, and this ensures that no inequality constraint violations, meaning when h of x is greater than 0, right? Making sure that those violations don't flip signs to present as a benefit. If we're working on minimization, right, we want h of x greater than 0 to be positive, right, because that presents a penalty to the objective function. Next, we have complementary slackness, and this is probably one of the more interesting ones. What it says is that for any optimal state, the product of mu and h, okay, must equal 0. And this is for the optimal state. And so we have two potential options, right? One can equal 0, or the other can equal 0, or potentially both. So let's talk about the first case, which is an active or binding constraint. For an active or a binding constraint, what we see is we're assuming, or we know, that h of x equals 0, and therefore its associated mu, a Lagrange multiplier, can be anything greater than 0. And this is telling us that the constraint has hit its limit. So let's say the constraint is on, the maximum number of trucks you can use to ship something. You've hit that constraint. You're at the maximum number of trucks. Then we have an inactive or non-binding constraint, and that's one which has not hit its threshold. And since h of x is greater than or equal to 0, less than or equal to 0, we know that mu has got to be equal to 0 in order to maintain the product of those two equal to 0. So complementary slackness is definitely one that you want to pay attention to, and one we're going to use heavily later. So here we show the KKT conditions in a symbolic or a mathematical form. Stationarity, again, if we take the derivative or the gradient of the Lagrange function, which is what we have below, with respect to x, that should be equal to 0. Now note, we're only taking it with respect to x, not with respect to lambda and mu, which is a slight tweak from how we did things in the first module, but you'll see that the same equations show back up. Okay, so stationarity requires us to take that derivative. Then we have primal feasibility. Again, for all the g equality constraints, they must be equal to 0. And for h, all of the inequality constraints, they must be less than or equal to 0. Dual feasibility, again, says that all of the mu values must be greater than or equal to 0. And complementary slackness says that once we have a solution, for that solution, the product of mu and the product of h should equal 0. Again, a couple notes up here. Remember, we're playing it pretty loose with our superscript and subscript indices. So if you have a rank 1 array, the superscript and the subscript both really mean the same thing. It's just what element we're talking about in a given array. So, how do we practically implement this process? And that's pretty difficult to explain. So I like to use an example. I think that's the best way to show this. So consider the example down here below. We're trying to minimize an objective function, which is x1 squared plus x2 squared. Again, these are just the indices. It's subject to a constraint, equality constraint, that x1 plus 2x2 minus 5 equals 0. It's subject to two inequality constraints. One is that x1 squared plus x2 squared minus 5 must be less than or equal to 0. And then a second inequality constraint, which says that essentially x2 must be greater than or equal to 0, but we've put that in terms of a less than or equal to inequality constraint by multiplying it by -1. Okay, so this is the example problem that we're going to use to demonstrate how the KKT conditions may be practically used. All right, so let's break this down to steps. So first we're going to define the Lagrangian or the Lagrange function. We already know how to do this. It is going to be f of x plus lambda times g of x. Now if we had more than one equality constraint, then we would have more than one lambda, but we don't. We have mu1 times h1 plus mu2 times h2, and we really are just taking all the pieces from the previous slide and plugging them in here. If you see up in the right hand corner these QR codes, these are just generally some references that I've used in case you want to check them out. I'll try to put them in the description as well. Okay, next step is to state the KKT conditions. We begin with stationarity, and for that we need to take the derivative of the Lagrangian with respect to both, well, all of the decision variables, in this case both x1 and x2, and what we end up with are these two expressions. Primal feasibility. Here we're simply listing out our equality and inequality constraints. So we have three elements here, g1, h1, and h2, and we just copy. Then we have complementary slackness, which says that the product of mu and h, and I didn't explicitly say, but that's for the optimal solution, the product of mu and h must be equal to 0. All right, so now we've stated the conditions. What do we do next? We need to analyze all potential situations or cases for complementary slackness. Because if you look back here, you see that for each one of these inequalities, there's two potential cases, right? We can have a case where mu is 0 and h is not equal to 0, or vice versa, right? So every inequality constraint has two potential states or cases. The fact one being binding, where h is equal to 0 and mu is greater than or equal to 0, or non-binding, where h is less than or equal to 0 and mu is equal to 0. So for these two cases, one is equal to 0 or is known to be equal to 0, or the other is known to be equal to 0. Now, because this example has two inequality constraints, we have 4 cases to analyze, or 2 to the n, where n is 2. The next step, after we've analyzed, is going to be to verify that all the KKT conditions are satisfied. So we're going to be using the KKT conditions to solve, and we're also going to be using them to verify our answer. So any violation or conflict makes the given case infeasible. And these conflicts can be something as simple as 4 equals 5, right? We could be analyzing or evaluating an expression and end up with, something like 4 equals 5, where obviously that's infeasible. And then step number 5, if we have more than one solution that's generated, we may need to compare their respective outputs that they generate from the objective function f. All right. So like I said, we have 4 different cases to look at. And so I'm going to call them attempts. Right, so the first attempt, or the first case of complementary slackness, is shown here. In the first case, we assume that both of the inequalities are binding, so they're both equal to 0. Now what we've done down here is we've adapted our KKT conditions slightly. We're actually going to start from the middle and then move up and down. So the first thing that we did was we know that the bound inequalities will transform to equalities. Originally, these were less than or equal to, all right? But now, because we've assumed that h1 is equal to 0 and h2 is equal to 0, these become equalities. I replaced the complementary slackness with really more of the dual feasibility condition, because now we know that mu 1 and 2 must be greater than or equal to 0, and there's really no need to write out, this full thing right here, because we know, at least for the first assumption, h is equal to 0 and mu is not. All right, so we've set our initial assumptions, or we've adapted the KKT conditions to coincide with our assumption which is stated right here. Why do we choose this one first? No reason, right? We can do them in any order. Okay, so what do we do next? Step 3B is we're going to, well, first we're going to look for opportunities. I mean, there's really no set mathematical method here. You have to use your algebra skills in order to solve. If I take a look back here, I can see that there's an opportunity to solve for x1 in this expression because we know x2 is equal to 0 and x1 is the only unknown. So that's what we did. We solved for x1 and we end up with square root of negative 5. Now, what could we do next? I see another opportunity up here, which is associated with our equality constraint, g of x. We know x1 and we know x2, and so we can check whether that equality constraint is satisfied. Because if it's not, then we have a problem. Okay, there's no need to continue any further. And so you can see here there is a problem, right? We end up with x1 plus x2 minus 5 equals 0, or should equal 0, but that gives us the square root of 5 plus 0 minus 5, and that is obviously not equal to 0. And so this case is unfeasible, so we can go ahead and mark it off as no longer being an option. Second attempt. And what we need to do is define a new assumption associated with complementary slackness and return to step 3A. So for this case, we are going to assume that only H2 is binding. So that's going to be this one down here. If H1 is not binding, that means its corresponding mu value must be equal to 0, right? Because the product of both of these must be equal to 0. If H1 is less than or equal to 0, then mu1 must be equal to 0, and that's just dictated by complementary slackness. So what changes do we make here? Well, we do transform H2 from an inequality to an equality constraint, and we can also lock in the first mu value as being equal to 0, right? We know the inactive coefficient equals 0. Unlike the last problem, the last case, we don't do anything to H1. That remains an inequality. So what do we do next? Like I said before, we have to use our algebra skills in order to try to solve this and look for opportunities to calculate more values. Doesn't really seem like we can use H1, right? Because that's an inequality and it doesn't provide us a very meaningful result. However, we do have g of x. Okay, and if we assume we know x2, then we can calculate x1 from that g of x, and that's what we do next. So we end up with x1 equals 5. And now how can we use that new information? We see that although h1 is an inequality constraint, it doesn't necessarily allow us to calculate any new values, it can allow us to check whether these values of x1 and x2 are at least feasible. If they're not, then there's no reason to continue down this path any longer. So let's go ahead and plug this in here and plug this in here. And what we end up with is 5 squared minus 5. 25 minus 5 is equal to 20, which is not less than 0. And so we see that this case is also unfeasible. Now we could go and check dual feasibility as well, but we've already found that there's a violation, so there's no need to do that. Third attempt. Again, to find a new case or a new set of assumptions for complementary slackness and return to step 3A. So for this case, we're going to assume that neither one of the constraints is binding. That means that both H1 and H2, right, are both less than or equal to 0. And in order to maintain complementary slackness, mu1 must be equal to mu2 must be equal to 0. For this case, most of the assumptions are included in the dual feasibility or complementary slackness category at the bottom. We know that both those inactive coefficients will be equal to 0, and we're not going to make any changes to H1 or H2. Those will both remain inequality constraints. Now, if you look, you'll see we have to deal with this one a little bit differently. There's really not too much we can do with G here because we don't know X1 or X2. However, there are some places we can use this information, right? We can use mu1 here, we can use mu1 here, we can use mu2 here. And perhaps if we make those substitutions, it'll give us some interesting results. So I plugged in those values, and what we end up with is essentially, let's see, lambda is equal to negative 2x1, and lambda is equal to negative x2, right? And then we could set these two equal to one another, and what we end up with is this expression. We see that 2x1 is equal to x2. All right. Now, is there any place that we can use that information below? There is. We can plug it into our equality constraint g of x and replace what was an x2 right here with its corresponding x1 value, which puts that expression in terms of x1 only, which allows us to solve. Okay, first we would solve for x1 because we have 5x1 equals 5, so obviously x1 is equal to 1, and then x2 would be twice that, so we end up with a value of 2. And now we have values for decision variables. We can plug them in here to these constraints and see if they're satisfied. If they are, then we could potentially have a viable solution. All right, so let's test it. So we plug it in here, we end up with 1 squared plus 2 squared minus 5. That equals 0, which is less than or equal to 0. Good. And then negative 2, or negative times 2, gives us negative 2, which is less than 0. And so step number 4, we finally get to that, and we observe that this case is feasible. It satisfies all the KKT conditions. There's no need to check dual feasibility because we already assumed that both of those values were equal to 0. And then last step here, it's not really 3F, I guess it would be 6, but I did use an exhaustive search in MATLAB just to check our answer, just to hedge our bets. And it did yield the same solution of 1 and 2. Now we could do a fourth attempt. I'm getting a little bit tired of doing the same steps over and over again. Essentially, we would end up with an infeasible or an unfeasible solution in the same manner as what happened for the first and the second. We've observed that KKT represents a set of conditions that define a feasible solution to the inequality constraint optimization problem, right? It doesn't necessarily define a complete method, as reconciling the KKT conditions may be difficult for more complex problems. And we saw that in our example where we do have to apply some algebra skills in order to solve for those values. Now, obviously, MATLAB can help us with that. And the next section, module number 3, is going to examine an alternative, some would say a more efficient way to integrate the inequality constraints into the method of Lagrange multipliers that we learned about in module number 1, which was only suited for the equality type constraints.